Now we're going to examine a very important kind of series, namely geometric series. And before we can talk about geometric series, we have to talk about geometric sequences. And a geometric sequence of common ratio r, where r is a constant, is something that looks like that. You have a first term, let's call it a, and then to get the next one you multiply by r, then to get the next one you multiply by r again, get the next one you multiply by r again, and you keep going that way. So you end up with the first term multiplied by powers of r. So one standard way to write it, if you start with a, the first term, and r, the common ratio, and your sequence starts at 1, then it would be, the general term would have the form a multiplied by r to the n minus 1, so that when n equals 1 you get r to the 0, which is 1. And gives you a. When n is 2, you get a times r, and so on. So let's look at some examples. Let's start with this sequence, 5, 10, 20, 40, 80, 160. Well, you see that each time to go from one term to the next, you just double it. You multiply by 2. So that means that we have a geometric sequence of common ratio 2. Right? The expression common ratio, because one way to find the common ratio is to take a ratio of the form an plus 1 over an. So for instance, I can take the second term divided by the first term, that's 10 over 5, that's 2. If I take another ratio of that form, let's say the third term divided by the second term, 20 over 10, that's 2. And then the fourth term divided by the third, 40 over 20, that's 2. And so this is a constant ratio, it's always 2. One way to write it in standard form is then 5 multiplied by 2 to the n minus 1, where n starts at 1, because 5 is the first term and 2 is the common ratio. But we could also write that, for instance, as 5/2 multiplied by 2 to the n if we want the power to be with index n instead of n minus 1, and here we would still start at 2. Of course, this is the same thing because 2 to the n over 2 is just 2 to the n minus 1. But we could also write that 5 multiplied by 2 to the n, but starting with n equals 0, in which case we get again the first term is 5, the second term is 10, and so on. So there are various ways of writing the same geometric sequence. Okay, let's look at a sequence that starts with 4, negative 2, 1, negative 1/2, 1/4. You see that from 4 to negative 2, you can think of it as dividing by negative 2. From negative 2 to 1, again, you divide by negative 2. From 1 to negative 1/2, you divide by negative 2. And then if we keep going, we get 1/4 and then negative 1/8. So we have a geometric sequence of common ratio negative 1/2. In this case, the first term is 4. So one way to write it would be in the standard form. We start with the index at 1. The first term is 4. The common ratio is negative 1/2. So we get 4 times negative 1/2 to the n minus 1. Another way to write it would be to say this negative 1/2 to the n minus 1, I can write that as negative 1 to the n minus 1 divided by 2 to the n minus 1. If I write 4 as 2 squared, and I have 2 squared over 2 to the n minus 1, that's 1 over 2 to the n minus 3. And so, therefore, we get another possible expression by taking negative 1 to the n minus 1 multiplied by 1 over 2 to the n minus 3. So again, there are various ways of writing the same geometric sequence. So if we have a geometric sequence of common ratio r, we have seen that it has this kind of form where a is the first term. Here a and r are of course constants, and the index n is the only thing that changes. So this is the standard form for our geometric sequence of common ratio r and first term a. And a first observation is that if the absolute value of the common ratio is strictly less than 1, then I'm taking powers of something strictly between -1 and 1. And when you take powers of that, you get closer and closer to 0. You get numbers that are in absolute value smaller and smaller, and so the limit of r to the n is 0. And so when I multiply by the constant number a, here I'm assuming that a is not 0, even though for that particular point it wouldn't matter, then the limit of a r to the n minus 1, the limit of our geometric sequence, is 0. If the absolute value of the common ratio is greater than 1, well, then I have powers of, let's say, imagine you have a number greater than 1 and positive. When you take powers, you get numbers that are larger and larger. Multiply by a constant a, you get something divergent. Assume now that it's negative. When you take the powers, in absolute value, you're going to get something that gets larger and larger, but the sign is going to alternate as you get even or odd powers. Regardless, we're moving towards the ends of the real line, and the sequence is divergent. If the common ratio is 1, then we're looking at powers of 1, which is always 1, so here we have a constant sequence. And if r is -1, then we get something of the form, well, I should have written -1 to the n minus 1, but it doesn't matter. In any case, you just have a that you multiply alternatively by 1 and -1, so you get a sequence that alternates between a and -a, and that is divergent. So now we turn to geometric series, which by definition is a series whose sequence of general terms is a geometric sequence. So that means it's a series of that form, sum from 1 to infinity of a standard geometric sequence, in other words, something of the form a r to the n minus 1, where a and r are fixed constants, and I'm going to assume that a is not 0, and n is the only thing that changes. So a basic observation is that when the common ratio r is in absolute value greater than 1, the sequence of terms is divergent, and we've seen that if the sequence of terms does not go to 0, then the series is divergent. So here our geometric series is going to be divergent in this case. And similarly, if r is 1 and a is not 0, then the limit of the sequence of terms is a, which is not 0, and therefore the series is divergent. Similarly, when r is -1, the sequence of terms is divergent, in particular it doesn't converge to 0, so the series is divergent. When the absolute value of the common ratio is less than 1, the limit of the general term is 0, but that doesn't tell us anything about convergence. So we know that it's necessary for the series to converge, that this limit be 0, but it's not enough. However, we will see that in this case it is enough. We were going to take a closer look at what happens in the case where the common ratio is in absolute value less than 1 in a moment. So what we have seen, at least for now, is that a geometric series is always divergent if the absolute value of the common ratio is greater or equal to 1. Now let's look at examples before we turn to the case where absolute value of r is less than 1. Let's look at the series from 1 to infinity of e to the n over 3 to the n minus 1. One way to rewrite that is, in order to get the same power for the top and the bottom, I'm going to rewrite e to the n as e multiplied by e to the n minus 1, and then write e to the n minus 1 over 3 to the n minus 1 as e over 3 to the n minus 1. And rewritten under that form, we get a standard form for geometric series where we have the first term e, and then the common ratio e over 3 raised to the power n minus 1. So this is a geometric series, and we know the common ratio. Let's look at the series that starts with 1/8 and then -1/4, plus 1/2, minus 1, and so on. Then you see that this is a geometric series of common ratio -2. because to go from one term to the next, you multiply by -2. And that means that in standard form, we would have the series from 1 to infinity of the first term, 1/8, multiplied by -2 to the n-1. Another way to write it would be to write this -2 to the n-1 as -1 to the n-1 times 2 to the n-1. -1 to the n-1 can also be written -1 to the n+1 if I feel like it, because if I switch the power by 2 for a power of -1, I get the same value. And then I have 2 to the n-1 divided by 8. 8 is 2 cubed, so I get 2 to the n-1 over 2 cubed, that's 2 to the n-4. That's another way to write the same series. So you see that depending on whether the series is given to you in standard form or not, it might not be that transparent that this is a geometric series and what the common ratio is. So you may have to manipulate it a little bit. Typically the easiest way to see it is to write out the first few terms and then look at the ratio of two consecutive terms. Now let's look at a series that starts this way: 1 plus 0.4 plus 0.16 plus 0.064 and so on. Then you see that we start with 1, then the next term is 0.4, so that we can think of it as 1 times 0.4. Then we have 0.16, which is a square of 0.4. Then we have 0.064, which is a cube of 0.4. And so we have geometric series of common ratio 0.4, where the first term is 1, and so we can write it as a sum from 1 to infinity of 0.4 to the n-1. Now let's look at another example that really you can think of as a geometric series, and it's a kind of geometric series that you've been dealing with for a long time without really knowing that you were manipulating a series. Let's look at the number whose decimal expansion doesn't stop, is periodic. Right? So I'm going to write that with as 0.73 with a bar over the 73, which means that the two-digit 73 keep repeating in the decimal expansion of that number. So I get 0.73, 73, 73, 73, and so on, and it never stops. Okay, so you know numbers like that. For instance, if you take 1/3, then the decimal expansion is going to be 0.33333, and so on. So I claim that we can think of that as a geometric series because this 73 here, the 7 is in the place for the 10th, the 3 in the place for the hundreds, so this 0.73 is really 73 hundredths. And then I add to it this 73 that is in the place of thousands and tens of thousands, and that's really 73 over 10,000, which I can think of as 73 over 100 squared. Then I have 73 where the places are hundreds of thousands and millions, and so I can think of that as 73 over 100 cubed, and so on. So what we have here is really the sum of a series starting from 1 to infinity of 73 multiplied by 1 over 100 to the n, which is a geometric series of common ratio 1 over 100, and first term 73 over 100.